ぼちぼち退院していただけるかなという段階まで来ています。
How did it feel for you personally?
我々はとにかく、心臓移植や人工心臓の治療をしながらですね、なんとかどの方も助けたいところがやっぱり悔しい思いっていうかですね、残念な思いをたくさんしてきましたので、2000年からですね、再生医療の研究開発を始めたんですね。ようやく人に応用するという意味での最初のステップを踏み出すことができたというふうな気持ちでは、私個人的にはアポロ11号がアームストロング船長によって月面で第一歩踏み出したぐらいの第一歩かなとは思います。
The human body begins as a fertilized egg, which is a single cell. It divides and multiplies, and eventually develops into body parts such as the brain, limbs, and organs, each responsible for certain functions. Creating iPS cells involves reprogramming existing cells into an embryonic-like state. iPS cells can develop into any type of cell. There are high hopes that this technique will make it possible to reproduce organs and tissue damaged by disease or injury. iPS cells are formed by introducing certain genes into existing human cells. In 2007, researchers succeeded in generating them from human skin cells for the first time in the world. As a result, Professor Shinya Yamanaka won the Nobel Prize for Physiology or Medicine in 2012. Sama's research team has been working with Yamanaka since 2008 to find a cure for heart disease using iPS cells. The tiny white dots are iPS cells. It takes about 1 month to create sheets of heart muscle cells from them that can be transplanted into patients. To accomplish this, the iPS cells are first multiplied. Microscopic footage shows new cells forming. When a special agent is added under certain conditions, they start developing into heart muscle cells. By day 9, there is movement, signaling the formation of a heart muscle cell. A large number of heart muscle cells must be produced for a transplant. In order to do that, various circumstances must be met. It took researchers about 3 years to figure out optimal conditions, including temperature, pH values, oxygen levels, and the timing of adding the agent. The iPS cells will only turn into heart muscle cells if these conditions are met.
そうですね、企業技術ですね。
体温に近いとかあるんですよ。
まあそこはご想像にはまるでしょうし、それも変えてますので、温度をある時間タイミングでまた変えたりしています。
Surprisingly, as the process advances, muscle cells are not the only cells that are created. Various other types of cells necessary for the heart to function form spontaneously.
生命の起源にも近いし、神秘的なところでもあるような気がしますね。
The cells stick together and form clusters. Sheets are created with these clusters.
早皿に巻くとこれにくっつくんですね。
Then, the cells all start moving together.
この中にですね、実は最も強い電気を出すペースメーカー細胞っていうのがあってですね、その細胞に合わせてみんな一緒に動くんです。だからオーケストラみたいなものです。みんなそれに合わせて一緒に動くという、これがもしバラバラだったら不整脈になって人間は生きていけないんですね。
So basically then the pacemaker cell is the conductor of
Yes.
the that's
その通
incredible.
りです。細胞同士がこういうコミュニティを作って一緒に動いてる、そのままに心臓に移植することはどれほど細胞にとってカンファタブルかと、そういうことを臨床で実現でき、第一例目の患者さんの手術できるようになったということですね。
I mean, it's like a science fiction movie. I mean, it seems so inconceivable, and here it is in 2020 that you perform this successfully.
Yes.
Amazing, absolutely amazing. And Professor, why do they have to be sheets? Couldn't you fundamentally just inject, for example, the iPS cells directly into the heart tissue?
注射器で注入するとですね、8割9割は死んでしまうんですね。死んでしまった細胞っていうのは塊を作って障害物みたいになるので、心筋がこうやって電気でガーッとこう動きてる中に障害物を入れたら、ここでよどむんですね、止まるんですね。そうするとそこに不整脈を起こす原因になるんです。シートは心の上をカバーして、障害物にならないので不整脈を起こさない。
Cultured cells can't live long after they are taken out of the culture medium. They signal a distressed state soon after the transplantation. The heart receives the signal and begins forming blood vessels to help these cells, which are on the sheets. About 12 hours later, the blood vessels connect the cell sheets to the heart. The cell sheets in turn send various substances through the blood vessels to the heart to support its functions. Researchers believe this process revives the weakened heart and restores it. Sawa will conduct a trial on 10 people. He aims to achieve clinical application in 3 to 5 years.
And what's your ultimate goal or your ultimate hope or dream with the iPS cell treatments?
もちろん、最終的にはですね、本当にたくさんの方がこれ治療で治る、そしてやはり心臓移植や人工心臓が完全になくなるとは思わないんですが、少しでもですね、それに至らないようにたくさんの人がこの治療を受けて元気に社会復帰してくれることがまずはゴールかなと思います。その上で投与方法もそうだし、細胞の数もそうだし、いろんな方法を変えていくことによってですね、より高い効果を目指す。最初にライト兄弟が丘から落ちたのか飛んだのか300メートル飛んでますよね。それぐらいですよね、今最初から太平洋を渡るような ジェット機を開発することはできないんですが、でもやっぱり最終的にはそうやってジェット機が世界を回る、もちろん宇宙にも行くような、そういうものも開発されていく、その段階の最初のステップとして今こうだけど、将来やっぱり大きくどんな人も助かるようにというふうになってほしいなと思います。
But it's a very close future. I mean, you're saying 3 to 4 years potentially before it could become available.
そうですね。
iPS cells are also giving hope to people with spinal cord injuries, for which no effective treatments have been found. Currently, there are said to be as many as 500,000 cases per year worldwide. Among them is Makoto Ohama. He heads a group for people with spinal cord injuries. He's completely paralyzed from the neck down and feels no sensation. Ohama was in his 20s when he injured his spinal cord. He was tackled during a rugby match and fell to the ground head first.
整形のドクターから、これは一生かかっても治ることないんですよって言われましたね。
The spinal cord is a bundle of nerves that runs through the backbone. It carries messages from the brain that allow the body to move. It also passes signals from the body to the brain about sensations. A spinal cord injury is damage to these nerves that leads to paralysis in the body. It can result from an accident or other causes. It is difficult for the damaged network or dead nerve cells to regenerate on their own. Doctors have yet to find an effective treatment. The damage spreads further due to inflammation and bleeding in the affected area. Ohama's spinal cord suffered severe damage at the neck, leaving him paralyzed below that area. Paralysis affects different parts of the body depending on the location and severity of the injury. The closer the injury is to the brain, the worse the paralysis will be. In some cases, even breathing becomes difficult. Ohama needs care around the clock. He suffers from poor blood circulation because of his immobility and needs to have his body shaken frequently.
やっぱり今自分で食事もできないじゃないですか。やっぱり食事ぐらい自分でしたいですよね。それが正直な思いで、やっぱりなんていうのかな、目の前にこう何かあっておかずが出てきて、やっぱり自分の食べたいものを自分でやっぱり食べたいとか、それからやっぱり文章を書くにしてもやっぱり自分の字で書きたい。だからやっぱりそこのところに戻りたいですよね。やっぱり手は使いたいですね。
Ohama has high hopes for a treatment using neural stem cells made from iPS cells. A clinical trial of it is due to begin in Japan this year. Professor Masaya Nakamura, an orthopedist, will lead the trial.
どうして骨を治せるのに脊髄は神経は治せないんだっていう、その思いがずっと、心の中にくすぶっていて、で、当時はみんな多くの先生たちは、いやそれは無理だ、そんな時間の浪費になる厳しい研究だよ、やめた方がいいっていう方もいっぱいいらっしゃったんだけど、僕はやっぱりどうしてもそこを直したいという思いで、研究を始めたっていう。
The spinal cord is as thick as a finger, and the damaged area can be very small. Nakamura plans to inject 2 million neural stem cells made from iPS cells directly into the damaged area. What's characteristic about this treatment is that it involves the transplantation of neural stem cells, which serve as a base for nerve cells. Depending on the location of the area into which the neural stem cells are transplanted, they will each turn into neurons and myelin sheaths, which cover the axon. Once a network of nerve cells is established, information can travel smoothly between the brain and the body. It makes possible the reconstruction of a damaged neural circuit, which was considered almost impossible until now. Patients with complete paralysis who injured their spinal cords 2 to 4 weeks beforehand will be selected for the trial. But Nakamura hopes to someday make the treatment available to patients who have suffered for longer periods, such as Ohama.
今回の例えば iPS 細胞をね入れたら完全のショーは急に立って歩くんですかって言われると僕はそれをはいとは言えない。だけど小さくても僕は大きな一歩だと思ってる。僕の中では積損の人たちにとってはもし指がね動かない指がもし動いたらコンピューター操作できるんですよね。だからもちろんその一般の方から見れば小さな一歩かもしれないけど僕は大事なことは一歩一歩着実に前に進める。損傷された脊髄の一髄節一つでも二つでも再生を促すことによって一見見たところは些細な変化かもしれないけどその積み重ねがね最後はそういった寝たきりの患者さんや車椅子の患者さんがいずれは立って歩けるようなそのゴールに向かってね進んでいけるんじゃないかなと思っているので。
In February 2020, Ohama and other members of his group held a symposium on the iPS treatment. Many people with spinal cord injuries are forced to cope with restrictions in their daily lives for many years. Nakamura was invited to talk about whether iPS treatment can give hope to long-term sufferers.
もちろんこれが第一歩、大きな第一歩になるのは間違いないです。始まりますから。だけど僕たちのファイナルゴールはもちろん慢性期の完全積損です。その私たちの思いも受け止めて皆さんも今頑張ってくれたらなとそう思ってます。ご清聴どうもありがとうございました。
普通に自転車に乗ってみたい。本当風を切って漕いでる自分の姿、それを今すごくしたいなっていうふうに思ってます。
これ再生医療っていうのは実現してほしいなと思いますね、自分的には。
本当にここまでやってきましたって感じですね。この治療が本当に慢性期の治療に入ってもらいたいし、やっぱり期待してますね。
Nakamura plans to begin a clinical trial on 4 patients as they undergo rehabilitation. He will monitor them for 1 year to confirm the treatment's safety and efficacy. It's been more than a decade since iPS cells were first produced, and research on them is expanding. In 2020, clinical trials will be launched in Japan for transplants of iPS-based cells to treat 3 other conditions, including damaged knee cartilage and blood disease. We asked Junya Toguchida, one of the people responsible for iPS research in Japan, about the challenges and prospects of this new treatment.
There is some risk of developing cancer. What causes this risk to rise?
Risks could arise when producing iPS cells, and also when culturing iPS cells into the cells we want to transplant. Errors in copying genes occur at a certain frequency when cells multiply. But the genes affected by these errors do not always become cancerous. If we culture them for long periods, the risk of errors rises. So we need to shorten the periods as much as possible.
Transplant rejection poses another challenge. All IPS cells used for the treatment are produced at Toguchida's lab to cut costs and ensure quality. They are made from cells taken from healthy people rather than the patients themselves, making rejection more likely. Most patients need to be given drugs to reduce that risk. We asked Toguchida about the prospect of overcoming this issue.
A day may come when people will consider having their own iPS cells made if it were to cost just 1 million yen, for example. But the question is when the cells will be needed. Imagine that a 20-year-old who has had iPS cells made gets liver cancer at the age of 60 and needs to have the organ removed. He would need a new liver made from the iPS cells, but this means the cells would have to be stored somewhere for 40 years. That would cost a lot of money.
I guess in the storage process, and that's going to be the biggest issue.
That's correct.
So thank you so much for your time. Arigatou gozaimasu.
Lớp còn thức không? Hello.
Dạ có nghe.
Rồi. Thì đó là những cái thành tựu mà chúng ta thấy là về iPS cell hoặc là stem cell mà ứng dụng cho cái liên quan tới các cái điều trị cho bệnh cơ tim. Hồi nãy chúng ta thấy là tóm lại chúng ta thấy á, những tế bào cơ tim chúng ta có thể làm được, có thể tạo ra những cái khúm tế bào và nó có thể tạo thành nhịp đập y chang như là những cái tế bào cơ tim mà trong cơ thể chúng ta. Tuy nhiên thì hồi nãy chúng ta thấy là phần lớn khi mà chúng ta bơm những cái khúm tế bào đó trong cái cơ thể chúng ta thì 90% nó là chết hết. Và chúng ta phải giải quyết những cái hậu quả của những tế bào chết đó, nó sẽ tiết ra nào là những cái độc chất thải, hoặc là những tế bào chết đó nó có thể recruit những cái hệ miễn dịch, nó làm cho tăng cường hóa cái hệ thống việc mà phản ứng viêm. Vâng, thì người ta mới nghĩ đến cái hình thức là người ta tạo một cái miếng sheet, miếng đó nó có thể là đưa những cái tế bào lên nha, tế bào cơ tim lên, vẫn định hình cái tế bào cơ tim. Thì miếng sheet đó là nó có thể là tổng hợp từ hyaluron hoặc mình tổng hợp từ cái sợi chitin. Chitin là nó có trong vỏ của cua, tôm cua. Thì cái vỏ tôm cua đó là hoàn toàn là nó không bị đào thải nha. Những chitin đó cực kỳ tốt, những cái sợi polymer sinh học cực kỳ tốt. Thì khi mà để tế bào lên thì các tế bào nó sẽ vẫn tạo ra những cái nhịp nó đồng bộ với cái tế bào cơ tim ở trong cơ thể, và thậm chí nó còn có thể là recruit được những cái hệ mạch máu để nuôi những cái tế bào này đó. Và đó là trong những cái hướng khá là thú vị cho điều trị những bệnh nhân mà suy tim, hoặc là những cái có dấu hiệu về liên quan tới việc suy giảm cái chức năng co bóp của cơ tim, hoặc là do những những cái tổn thương ở cơ tim do bị thiếu hụt các cái mạch máu để nuôi những tế bào đó. Thì những tế bào mà đã bị chết rồi, những cơ tim bị chết rồi, hoại tử rồi, thì khi mà đưa cái miếng tế bào gốc mà có chứa các cái tế bào cơ tim mà đã biệt hóa rồi, thì những cái tế bào đó nó sẽ hồi phục lại các cái mạch máu và hồi phục lại cái hệ thống cơ như cũ. Đó là cũng một cách khá là hay. Ngoài ra thì có cái ứng dụng liên quan tới việc tổn thương về đốt sống. Những cái bệnh nhân, những người mà chơi thể thao rồi bị chấn thương và sau đó là bị liệt hết người ở phía dưới, bị liệt hết toàn bộ toàn thân. Người ta thử nghiệm đưa những cái tế bào để mà có thể là nó ổn định, nó tạo thành những cái hệ thống ganglion cell trong cái hệ thần kinh. ngoại biên để giúp cho việc mà tái tạo lại cái hoạt động của các tế bào thần kinh ngoại biên, vân vân. Thì đó là những cái potential rất là lớn. Tuy nhiên chúng ta biết là nó sẽ còn nhiều cái thách thức khác. Thì để hiểu thêm thì chúng ta sẽ tiếp cái bài này